Good morning, everyone. My name is Faik Hussain. I am from Aeronautical Department, and my today's topic is about modeling space time periodic structures with arbitrary unit cells using periodic circuit theory. Introduction to space-time periodic structure. Here's an introduction to space-time periodic structure. Space-time periodic structures refers to the repeating patterns or arrangements of objects or events in both space and time. What are the key characteristics? Periodicity. The structure repeats itself at regular intervals in space or in time. Symmetry. The structure exhibits symmetry under translation in space or time. Order. The structure has a well-defined arrangement of objects or events. Examples. Crystals. Crystals have a periodic arrangement of atoms in space. Time crystals. Time crystals have a periodic arrangement of atoms or particles in time. Periodic lattices. Periodic lattices have a repeating arrangement of points or objects in space. Theoretical framework. Group theory. Group theory provides a mathematical framework for describing the symmetries of space-time periodic structures. Differential geometry. Differential geometry provides a mathematical framework for describing the curvature and topology of space-time periodic structure. What are these applications? Material science. Understanding space-time periodic structures is crucial for designing and optimizing materials with specific properties. Condensed matter physics. Space-time periodic measurement play a key role in understanding the behavior of solids and liquids. Optics. Periodic structures are used in optics to create devices such as diffraction, grating, and optical fibers. Quantum computing. Space-time periodic structures have potential applications in quantum computing and quantum information processing. Fundamentals of time periodic circuit theory. Time periodic circuit theory. It is a branch of electrical engineering that deals with the analysis and design of circuits that operate in a periodic manner. Key concepts. Periodic signals. Signals that repeat themselves at regular intervals. Time periodic circuits. Circuits that operate in a periodic manner, with their parameters changing over time. Floquet theory. A mathematical framework for analyzing time periodic circuits. Time periodic circuit analysis. State space representation. Representing the circuits using a set of differential equations. Floquet exponents. Calculating the Floquet exponents to determine the stability of the circuit. Harmonic balance. Analyzing the circuit's response to periodic signals using harmonic balance. Applications of time periodic circuit theory. Power electronics. Designing power electronic circuits that operate in a periodic manner. Communication system. Analyzing and designing communication systems that use periodic signals. Control systems. Designing control systems that operate in a periodic manner. Tools and techniques. SPICE. Use SPICE to simulate time periodic circuits. MATLAB. Using MATLAB to analyze and design time periodic circuits. Floquet theory software. Using specialized software to calculate Floquet exponents and analyzing time periodic circuits. Characteristics of arbitrary unit cells. Geometric characteristics. Shape. Arbitrary unit cells can have any shape, including polyhedra, polytopes, or other complex geometries. Size. The size of the unit cell can vary and it may not be uniform in all directions. Orientation. The orientation of unit cell in space can be arbitrary. Symmetry characteristics. Lattice symmetry. Arbitrary unit cells may not exhibit lattice symmetry, meaning that the arrangement of cells may not be periodic. Point group symmetry. The unit cell may exhibit point group symmetry, which describes the symmetry operations that leave the cell unchanged. Space group symmetry. The arrangement of unit cells in space may exhibit space group symmetry, which describes the symmetry operations that leaves the arrangement unchanged. Topological characteristics. Connectivity. Arbitrary unit cell can complex connectivity with cells connected in non-trivial ways. Genus. The genus of the unit cell can be non-zero, indicating the presence of holes or tunnels. Euler characteristics. The Euler characteristics of the unit cell can be non-zero, indicating the presence of non-trivial topology. Physical characteristics, material properties. Arbitrary unit cells can have very material properties such as density, conductivity, or optical properties. Boundary conditions. The unit cell may be subject to arbitrary boundary conditions, such as fixed or periodic boundaries. External fields. The unit cell may be influenced by external fields, such as electric, magnetic, or gravitational fields. Mathematical modeling of periodic structures. Mathematical representations. Periodic functions. Periodic functions such as sinusoidal functions are used to model periodic structures. Fourier series. Fourier series are used to represent periodic functions as the sum of sinusoidal functions. Differential equations. Differential equations such as wave equation are used to model the behavior of periodic structures. Modeling techniques. Finite element method. It is a numerical method used to solve partial differential equations that describes the behavior of periodic structures. Finite difference method. It is a numerical method used to solve partial differential equations that describe the behavior of periodic structures. Blocked wave analysis. Blocked wave analysis is a method used to study the behavior of periodic structures such as photonic crystals. Applications. Photonic crystals. Mathematical modeling is used to design and optimize photonic crystals, which are periodic structures that can control light. M- Metamaterials. Mathematical modeling is used to design and optimize metamaterials, which are periodic structures that can exhibit unusual properties. Structural mechanics. Mathematical modeling is used to study the behavior of periodic structures such as bridges and buildings under various loads. Software tools. COMSOL. COMSOL is a software tool used for modeling and simulating periodic structures. MATLAB. MATLAB is a software tool used for modeling and simulating periodic structures. ANSYS. It is a software tool used for modeling and simulating periodic structures. Time-dependent material parameters. Types of time-dependent material parameters. Viscoelastic parameters describe the time-dependent behavior of materials that exhibit both viscous and elastic properties. Creep compliance describes the time-dependent deformation of materials under constant stress. Relaxation modulus describes the time-dependent decreases in stress under constant strain. Dynamic modulus describes the time-dependent behavior of materials under oscillatory loads. Factors influencing time-dependent material parameters. Temperature. It affects the rate of molecular motion, influencing time-dependent material behavior. Moisture. It affects the material's property such as stiffness and strength. Aging. Materials can undergo changes in their properties over time due to aging. Loading history. The material's response to loading can depend on its previous loading history. Modeling time-dependent material parameters. Linear models describes the time-dependent behavior of materials using linear differential equations. Non-linear models describes the time-dependent behavior of materials using non-linear differential equations. Crony series, a mathematical representation of the relaxation modulus. Generalized Maxwell model, a model that represents the time-dependent behavior of materials using a series of spring dashpot elements. Replications of time-dependent material parameters. Structural analysis. Time-dependent material parameters are essential for predicting the long-term behavior of structures. Materials science. Understanding time-dependent material parameters is crucial for developing new materials. Biomechanics. Time-dependent material parameters are important for understanding the behavior of biological tissues. Polymer science. Time-dependent material parameters are essential for predicting the behavior of polymeric materials. Numerical techniques for analysis. Finite element method. It divides the problem domain into smaller elements, solves partial differential equations using a variational principle. Application. Structural mechanics, heat transfer, fluid dynamics. Finite difference method. Approximates derivatives using finite differences. It solves PDEs using a grid-based approach. Applications. Heat transfer, fluid dynamics, electromagnetics. Boundary element method. It solves PDEs using a boundary integral equation approach. Application. Structural mechanics, heat transfer, and fluid dynamics. Mesh-free methods. It uses a cloud of points to represent the problem domain. It solves PDEs using a weighted residual approach. Application. Structural mechanics, fluid dynamics, and heat transfer. Monte Carlo methods. Uses random sampling to solve problems. Applications. Uncertainty, quantification, optimization, statistical analysis. Applications in photonics. Space-time periodic structures have significant applications in the field of photonics, particularly in laser design. They can be used to create photonic crystals that manipulate light propagation. This leads to advances in optical devices, including filters, switches, and sensors. Application in acoustics. Similar principle apply in acoustics, where periodic structures can control sound waves. Acoustic metamaterials can be engineered to achieve negative refraction and sound clocking. These innovations open new avenues for noise control and sound manipulation technologies. Challenges in modeling and design. Modeling space-time periodic structures poses challenges due to their complexity and non-linearity. Ensuring accuracy in simulations while managing computational resources is a critical concern. Ongoing research aims to develop more efficient algorithms and modeling techniques. Future directions and innovations. The future of space-time periodic structures modeling lies in integrating machine learning and artificial intelligence. These technologies can enhance predictive capabilities and optimize design processes. Continued exploration of new materials and structures will derive advancements in this exciting. Thank you.